Good morning, class 11. We are studying the sixth chapter, chemical equilibrium. In past week, we had 3 classes in which we have learned the introduction of reversible, irreversible reactions and the state of chemical equilibrium. We also have learned the law of mass action and how to derive or write equilibrium constant expression for Kc. We also have learned how Kc and Kp, what are Kc, Kp and how they are related in another detailed way. Today we will continue the same lecture, and today I will teach you how can you calculate the equilibrium constant for any reaction. Right now we must first understand why we are trying to calculate the value of Kc. If we know the value of Kc, from there we can control the direction of the reversible reactions, because that is the task. Our task is to control the direction of reversible reactions. And Kc plays, the value of Kc, as you will see in future, plays a very strong role in determining predicting the direction of reaction and controlling the overall reaction. So we must understand Kc, and we must also calculate how to calculate Kc. So if you have initial concentration or quantities of the reactants, that will not help you to find Kc. You have to make sure that your reaction proceeds, reaches the equilibrium, and then the concentration at the time of equilibrium, when they are divided, Kc is the ratio of the product of active masses of the products to the product of active mass of the reactants, CD upon AB. These are not initial concentration, these are the equilibrium concentration. So if you want to really calculate the value of Kc of any reaction, you might need to take a reaction and make it reach equilibrium, and then calculate the concentration, the quantity of product as written at that time when the equilibrium was established, and then divide these values to find the value of Kc. So this way, every reaction will have its own value of Kc and could be used to control the reversible reaction. Now, these things I'm discussing right now may be not easy for you to understand. So we will take a reaction. Esterification we discussed already. An ester, ethyl acetate, forms when acetic acid and ethyl alcohol react together. This is a reversible reaction. Its introduction is being given to you already. Now what you need here? You need here basically several stoppered flasks. Conical flasks, stoppered flasks. If I have to explain to you here what is a flask. So a flask looks like this, right? This is called a conical flask. Now there are some flasks which have a stopper. There's a glass piece which inserts from the top, and it is called stoppered flasks or stoppered conical flasks. You need these flasks. You need 5 flasks. 5 stoppered flasks we need. Okay? Can you see it? Yeah. And then we need these chemicals, the acetic acid and ethyl alcohol. And equimolar, let's say 10 ml, 10 ml of each we drop in these flasks. So we have 5 flasks, right? So we have flask number 1, flask number 2, I'm sorry, excuse me for my drawing, flask number 3, flask number 4, and flask number 5. And the stoppered flask, it means once we close it, anything else cannot come inside, it will make it a closed system. Now we will add 10 ml of acetic acid and 10 ml of ethyl alcohol. Okay? So we add 10 ml of acetic acid and ethyl alcohol into the flask A. And we start a stopwatch. You know stopwatch, once you press it and the time starts. So we keep adding these reactants. These are the initial concentrations which we know, and Kc is independent of them. And we add to all these flasks and we start the stopwatch. Add the chemicals in the flask A, start the stopwatch. Leave it there. Chemicals into another flask, flask B, and start another stopwatch for flask B. So in this way you have 5 A, B, C, D, and E. You have 5 stopwatches running, right? Now you have to stop the reaction at different times, right? So that which one has equilibrium. Because we have to reach the equilibrium concentration, the quantities of the reactant and the products when the equilibrium was established. And we don't know when. So we will first, we will just consider 5 flasks and then we will stop these equilibrium, stop the reaction there. So let's say, let flask A, the contents react for 5 minutes. It's just a simple example. Flask B contents for, allow them to react for 10 minutes, 15, 20, 25. Every flask gets different time. So we have to see which flask has the actual equilibrium, all right? Because the reaction goes on, the reactants convert into products and then product to reactant, and there's one time where the both forward and reverse reaction are in the equilibrium. So we need this. Okay. How you stop equilibrium? You add ice, crushed ice. When we used to study in university, we had an ice box, and we used to actually eat that ice also, but we used to take them for stopping the reaction, or squeeze or seize or stop the reaction there. So A, 5 minutes, 10, 15, 20, 25 minutes. Now, when the equilibrium, we don't know where the equilibrium is achieved. So to know where the equilibrium is achieved, we need sodium hydroxide. Yes. We have to use the titration method. The titration method, basically, if you know titration, it's a method of calculating the quantity of an acid, method of calculating quantity of acid with a base, right? So acid base neutralize, and the amount of base consumed, it can be used in a formula, and then it can tell us the molarity and the quantity of the acid present in the flask. So first we need 2 chemicals, acetic acid, ethyl alcohol, and we need stopwatches. We need 5 stoppered flasks, and we have to add these chemicals to each flask and allow the reaction to proceed. Using a stopwatch, we can allow first vessel to to react for 5 minutes, the other for 10, 15, 20, 25, so on. And then we squeeze, or we stop, freeze the reaction by adding crushed ice into each, and then using the stoppers to stop it, And then we take sodium hydroxide in a burette, This is a iron stand. This is a burette. A burette is a very long glass tube. We fill in the base inside it. We take our Another flask, we take this flask, we add 2 drops of indicator, 2 drops phenolphthalein. This is indicator, right? It is colorless in acid and pink in base. So we have to see that does the entire 10 ml of acid is neutralized by NaOH or not. Okay, so we take flask A, put 2 drops of phenolphthalein. The color remains colorless. You just drop NaOH from burette. Pink color comes in. You shake it. Pink color is gone. And then you again add NaOH. Pink color comes and you shake it. Now you reach a point where the pink color stays. This is called the end of titration. This is a very long story. Please don't be confused. But the overall purpose is that we have to find that in which of these flasks exactly 10 ml of sodium hydroxide consumed shows a permanent pink color, because that flask will be our flask which will contain the equilibrium concentration, because that will be the equilibrium will be established in those. Because in the other flasks, either it will be going forward reaction or it will be going reverse reaction. So 10 ml of acetic acid will not be neutralized by 10 ml of NaOH. So you have to use flask A and B and C and D and E and find out which flasks shows pink color, permanent pink color for exactly 10 ml of sodium hydroxide. Our book does not have this information. Our book tells you that you can find the equilibrium concentrations by titrating the mixtures of the flask against NaOH. I have here explained the whole process to you, how you do it, okay? The book doesn't even tell you that there are 5 flasks, but I have done it experimentally, I have done myself. There are always 5 flasks, and we need stoppered flasks, we need phenolphthalein, the indicator, we need the sodium hydroxide for titration to finding out which flask has the equilibrium and the quantity of the equilibrium contents, and then we titrate them. So we first do like this, okay? Let us come over here back to the equation. So initial moles, okay? Initial mole. In the beginning of reaction, let us suppose you take A mole of acetic acid, B mole of ethyl alcohol. Since it is the beginning, neither the ester nor the water forms. This is the moles at initial state, or you can say initial moles. All right. Now this AB can be different. I can take 10 ml, you can take 10-20. Different students can take different quantities of acetic acid and alcohol. So these are initial moles and they are known, but they cannot directly calculate Kc. All right. Now once the equilibrium is established, okay, then it's called equilibrium moles. Yeah, moles at equilibrium state. What? Equilibrium moles. All right. So once equilibrium is attached, some unknown quantity of ester, X, and water is. Why X? Because we don't know what will be the X. Okay. How can we find X? To find X, we will basically do the A minus X. Like if acetic acid was 10 ml and at equilibrium it is 3 ml. So how much of it is consumed? 7. So that will be the ester. So if by titration, you know A and B because you take them in the beaker. You can find A minus X and B minus X by titration against NaOH. So the A minus X, the missing amount is X, is this thing, So you can calculate that way the quantity of these two. Now this is the equilibrium initial moles, this is the equilibrium moles, and now we need concentration, because concentration atom masses are in mole per dm cube. So we need equilibrium concentration. For that we take mole per dm cube. So it will be A minus X upon V, whatever volume you have taken, B minus X upon V, X upon V, X upon V. All the volumes are same. If you take 10 ml, 10 ml, 10 ml, because this is an equimolar reaction, 1 mole, 1 mole, 1 mole, and 1 mole. So this is the equilibrium. Now applying law of mass action. If you apply this law, then Kc will be active mass of ester, CH3, COO, C2H5, right? And water, and we divide it by CH3, COOH, and C2H5OH. Now, where there's these, the values will come in play. So it's going to be X upon V for ester, X upon V for water, and A minus X upon V for acetic acid, B minus X upon V for the alcohol. These V's basically cancel each other because they are equivolume, equimolar. They all are taken in the same volumes, so they will cancel each other, and we will end up with Kc is equal to X into X, X square, divided by A minus X and B minus X. Now this is a formula for calculating the Kc of this reaction. It means that A and B, 10 ml, 10 ml, 10 or 20, whatever known, different reaction, different values will come here. X is the quantity of the ester formed, which we can determine after the titration against NaOH. Put all these values here, you will have one value, one number, okay? You will have one answer. The ratio will be one answer. And for this reaction, the ratio is about 4. Now, if you take more A and more B, so X will also be more. The ratio will not change actually, right? So you can understand this one. I can show you in the textbook, like if you have this chart. One student took this mole of acetic acid. This is his A, this is his B. So X formed was this. When he divided them, like X square upon A minus X, B minus X, the answer was 4.04. Another student take like 63, this is his A, this is 23, he took the alcohol, different quantity. So he had X same, and when he divide them, answer is again like this, 3.88. So different reactions, different quantities of alcohol and acids will have different X values. These are the real values. The ratio will not change, the ratio will remain as 4. Once equilibrium is achieved, the ratio remains unchanged because now the concentrations do not change. So if you know the initial moles or concentration of the reactants, you cannot calculate the value of Kc. The only way to calculate the value of Kc is to find out the concentration at the time of equilibrium. And to do that, you have to do this entire process, okay? In which you take some amount of the alcohol, and it could be different reaction will have different values. So I will slightly help because the text here is a little bit confusing, you know. This is the reaction. So I want to basically help you read it for you, okay? So known masses, when you know A or B, whatever the values are, you know in your reaction. Of what? Acetic acid and alcohol, you take them in stoppered flasks. let's say A mole per dm cube was your acetic acid, B mole per dm cube was alcohol. When equilibrium establishes after some time, the contents, the things inside the flask cooled or quenched by adding crushed ice. It will stop the reaction to go any further, stop the equilibrium. So the equilibrium mixture contains unused reactants, left the A minus X and B minus X, as well as the products. Hence, the amount of acetic acid left at equilibrium will be determined by titrating it against the NaOH solution. Right? Suppose the amount of acetic acid is A mole per dm. Suppose the ester is X mole per dm cube. So it means that at equilibrium, the acid will be A minus X, alcohol will be B minus X. Since it's an equimolar reaction, 1 mole of each substance give 1 mole of the other, so the X is same. Like the amount of ester and the amount of water will be same because both reactants have similar moles in the chemical equation. So all these moles you put here, initial moles A, B, nil, nil, the A for acetic acid. This equation should be written as like here. So A is right under the acetic acid, B is right under the alcohol, nil, nil for them. Equilibrium moles, but we use active mass, so divided by volume, you know the Kc value, putting the values, we cancel, you have this equation. Now a different reaction will take different values of A or B, but their X will also be likewise. If I take more A and B, my X will also be more, so the ratio will remain same. If you take less A and B, the X will also be less, so the ratio will remain same. The ratio each time equilibrium is established for this reaction, it averages to 4. Right? It says that for this system, the value of Kc is averaging to 4. So you can have different reactions, you can have different products, me, you, everybody will take their own values, but the equation of Kc and the value of Kc will always be 4. Now, once we know that this reaction has a Kc value 4, using this value 4, we can do a lot of things. We can predict the direction of reaction, we can calculate the amount of products. In future, I will tell you the applications of Kc. So there you will find out that if you don't know the value of Kc of any reaction, how difficult it will be for you to predict the quantities or to predict the direction, whether it's going forward or backward or whatever. So this is your task for today. Please read from the book again, work it out, and then share with me your work. That's the important part. Sharing your work with your teacher is the most important part to understand these lectures. So we will end our lecture over here. On Friday, we shall have a written test in the presence of your parents. It will be good for you to also remember all these topics from now. All right. Thank you so much. If you have any question, you can send me a voice message because text message, the questions are not understandable. So any student can send me a voice message if he or she wants some more explanation from me on that topic. Thank you so much. See you tomorrow, same place. Bye.